Welcome to Omega Open Course. In this video, we are going to calculate the wavelength of the radiations emitted when an electron makes a transition from one stationary state to the another stationary state in a single electron species like hydrogen atom. In order to do this, first we need to calculate the total energy of the electron when it is in a particular stationary state or orbit. We know that the total energy of the electron in any orbit n is minus 2 pi square mk square e to the power 4 by h square into z square by n square joule, or minus E naught z square by n square joule. Here E naught is the total energy of the electron in first orbit of H atom. If we calculate the value of E naught, it comes out to be 13.6 electron volt. If you want to learn how the value of energy has been derived, click on the link shown or see the description below. Z is the atomic number of the single electron species and n is the number of orbit or stationary state in which the electron is present. Thus, the value of total energy of an electron in a species whose atomic number is Z and the number of orbit in which the electron is present is n is minus 13.6 Z square by n square electron volt. Using this formula, we can find the energy of electron in different orbits. Now let's take the example of hydrogen atom. We are going to calculate the energy of electron in different orbits. For first orbit, n is equal to 1. Therefore, E1, that is energy of electron in first orbit, is minus 13.6 Z square by n square electron volt. Here Z is equal to 1 and n is also equal to 1. Hence, E1 is equal to minus 13.6 electron volts. Similarly, E2, that is total energy of electron in second orbit of H atom, is equal to minus 13.6 by 4 is equal to minus 3.4 electron volt. E3 is equal to minus 13.6 by 9 is equal to minus 1.5 electron volt. E4 is equal to minus 13.6 by 16 is equal to minus 0.85 electron volts. E5 is equal to minus 13.6 by 25 is equal to minus 0.54 electron volts. E6 is equal to minus 13.6 by 36 is equal to minus 0.38 electron volt. For n is equal to infinity, E infinity is equal to minus 13.6 by infinity square is equal to 0. Thus, we have calculated the value of total energy of electron in different orbits of hydrogen atom. Now, let's have some discussion about the idea involved behind the calculation of wavelength of spectral lines, that is the wavelength of the radiations emitted. When an electron jumps from higher energy orbit to a lower energy orbit, an electromagnetic radiation is emitted in the form of a photon, and its energy is equal to the difference of the total energy of the orbits between which the electron is making the transition. The pattern of spectral lines obtained are called emission spectra. In case the opposite happens, that is, electron is jumping from lower energy orbit to higher energy orbit, then a photon of an electromagnetic wave of energy equal to the difference between the two orbits is absorbed by the atom. We call the spectral lines absorption spectra. The calculations involved are same as in the case of emission spectra. Let me clarify this idea by taking an example. Suppose the electron is in second orbit of H atom. Then total energy of electron will be minus 3.4 electron volts. And then electron jumps to the first orbit. Now the total energy of electron is minus 13.6 electron volt. The difference in energy, that is delta E, is equal to minus 3.4 minus 13.6 is equal to 10.2 electron volt. Therefore, the energy of the photon emitted during this transition must be equal to delta E, that is 10.2 electron volt. Now, we already know that the energy of the photon whose wavelength is lambda is equal to hc by lambda. One thing must be kept in mind. The energy of the photon calculated by this formula gives us the value in joules, whereas the value of delta E is in electron volts. So, we must either convert the hc by lambda value in electron volts or delta E value in joules before equating these two energy terms. This can easily be done. We know that 1 electron volt energy is equal to 1.6 into 10 to the power minus 19 joules. 1.6 into 10 to the power minus 19 is equal to the charge of an electron. Therefore, we often represent this value with E. And we can write 1 electron volt is equal to E joules. And therefore, delta E in electron volt is equal to delta E into E in joules and that is equal to hc by lambda. Hence we can write delta E into E is equal to hc by lambda, or lambda is equal to hc by E into 1 by delta E. Now on calculating the value of hc by E, we get hc by E is equal to 1242 into 10 to the power minus 9, and therefore we can write lambda is equal to hc by E into 1 by delta E is equal to 1242 into 10 to the power minus 9 by delta E meter is equal to 1242 by delta E nanometers. Now for transition from n is equal to 2 to n is equal to 1, delta E is equal to 10.2 electron volt. Therefore lambda is equal to 1242 by 10.2 nanometers is equal to 121.7 nanometers. Now let us summarize the above discussion and lay out the steps through which we can calculate the wavelength. Step 1 is to find the energy of two orbits between which the electron is making the transition. In our case it was second and first orbit. Energy of first orbit is equal to minus 13.6 electron volt. Energy of second orbit is equal to minus 3.4 electron volt. Step 2 is to find the difference of energy between these two orbits, that is to calculate the value of delta E. In our case, it is minus 3.4 minus 13.6 is equal to 10.2 electron volts. Step 3 is to divide 1242 by the value of delta E and we get the wavelength in nanometers. In this case, since delta E is 10.2 electron volt, lambda is equal to 1242 by 10.2 is equal to 121.7 nanometers. Using these simple steps, we can calculate the wavelength of any radiation emitted during the electronic transition in single electron species. In case of absorption spectra too, we follow the same steps. The only difference is that while in case of emission spectra, photons are emitted, whereas in case of absorption spectra, photons are absorbed. Now let us draw the line which represents the transition of electron from n is equal to 2 to n is equal to 1 on the energy diagram. For the transition from n is equal to 3 to n is equal to 1, let us find the energy of both the orbits from our energy diagram. We can see that E3, that is energy of the third orbit, is equal to minus 1.5 electron volts, and E1, that is the energy of the first orbit, is equal to minus 13.6 electron volts. And thus the value of delta E is equal to 12.1 electron volts. Therefore lambda is equal to 1242 by delta E is equal to 1242 by 12.1 is equal to 102.6 nanometers. And the line corresponding to the given transition is as shown. For transition of electron from n is equal to 4 to n is equal to 1, E4 is equal to minus 0.85 electron volt and E1 is equal to minus 13.6 electron volt. The value of delta E is equal to 12.75 electron volt. Therefore lambda is equal to 1242 by 12.75 is equal to 97.4 nanometer, and the line on the energy diagram is as shown. Similarly, other lines can be drawn on our energy diagram. This is the line for transition from n is equal to 5 to n is equal to 1, and this is the line for transition from n is equal to 6 to n is equal to 1. Now let us calculate the wavelength of the photon emitted when the electron makes transition from n is equal to infinity to n is equal to 1. From energy diagram, E infinity is equal to 0 electron volt and E1 is equal to minus 13.6 electron volts. And hence delta E is equal to 13.6 electron volts. And therefore lambda is equal to 1242 by 13.6 electron volt, which is equal to 91.2 nanometers. The corresponding line is as shown. When an electron jumps from any excited state to the ground state, as was the case in previous examples, the line is said to be of Lyman series. All the vertical lines shown in diagram represents the line of Lyman series. The line corresponding to the transition from n is equal to 2 to n is equal to 1 is the first line of the Lyman series, and the line corresponding to n is equal to infinity to n is equal to 1 is the last line or limiting line of the Lyman series. Since the energy of the photon emitted in the first line of Lyman series is smallest among all the lines of the series, the wavelength of the first line is the longest one. Similarly, the energy of the photon of the last line is largest, its wavelength is smallest. Now let's calculate the wavelength of the transition from n is equal to 3 to n is equal to 2. From energy diagram, E3 is equal to minus 1.5 electron volt and E2 is equal to minus 3.4 electron volt. And hence delta E is equal to 1.9 electron volt. Now lambda is equal to 1242 by 1.9 is equal to 653 nanometers. The corresponding line is as shown. For transition from n is equal to 4 to n is equal to 2, E4 is equal to minus 0.85 electron volt and E2 is equal to minus 3.4 electron volt. Hence, delta E is equal to 2.55 electron volt. And lambda is equal to 1242 by 2.55 is equal to 487 nanometers, and the corresponding line is as shown. Similarly, lines for other transitions can be drawn. Now let's calculate the wavelength for transition from n is equal to infinity to n is equal to 2. E infinity is equal to 0 electron volt and E2 is equal to minus 3.4 electron volt. Therefore, delta E is equal to 3.4 electron volt, and hence lambda is equal to 1242 by 3.4 is equal to 365 nanometers. And the corresponding line is as shown. When an electron jumps from energy level n is equal to 3 or higher to n is equal to 2, the radiations belong to the Balmer series. The lines of this series are also known as the lines of the visible region. N is equal to infinity to n is equal to 2 transition produces the wavelength which is called the last line or the limiting line of the Balmer series. Its wavelength is shortest in the Balmer series. N is equal to 3 to n is equal to 2 transition produces the wavelength which is called the first line of the Balmer series. Its wavelength is longest in the Balmer series. Similarly, when an electron from higher energy level jumps to n is equal to 3, the lines produced are known as that of Paschen series. They belong to infrared region. When electron jumps from higher energy level to n is equal to 4 and n is equal to 5, the lines generated are known as bracket and front series respectively. As can be seen from the energy diagram, the energy of the photons of the Balmer series is less than the photons of the Lyman series. Therefore, wavelength of the Balmer series lines is always larger than that of the Lyman series. This in nutshell is all about the spectral lines of the hydrogen atom. I hope this video was useful for the understanding of the radiations emitted in electronic transition of single electron species. If you have any question in chemistry, you can post it in comments section. We will post a video related to your question. Please like and share the video so that other students can find us. Subscribe the channel for more such videos and other updates. Thank you for watching.